Hi all, welcome to this lecture 7 of the lecture series Unconstrained Optimization. Today we are going to discuss continue discussing convex set from the previous lecture, and today we will discuss the lemma called Farka's lemma. It's a very important lemma which will help us derive the optimality conditions of various linear and non-linear optimizing functions, and we also will discuss one of its corollary and then we'll end the lecture. So before continuing with the lecture, let's see what we did in our last lecture. So in last lecture we defined what are convex sets. So convex sets are the sets in which if you take any 2 points in that set, then then all the points belonging to the line segment joining these 2 points also belong to the set. Then only it's called a convex set. So this is an example of a convex set. But if you take only the boundary of this set, let's say just this boundary, then let me redraw it. So if we take only the boundary of this set, then if we take any 2 points on it, you can see there are several there are points which do not belong to the boundary, so it's a non-convex set. Similarly, we can have a set like this. You will see if we take 2 points like this, then the line segment joining those 2 points, there are several points on those lines which do not belong to set. So this is also an example of non-convex set. So with this basic idea, let's move ahead and derive some of the results which will help us derive Farka's lemma. So before moving forward, let's state something called a theorem CS1. So what I'll do is I'll state the theorem and then I'll explain it geometrically, and then later on we'll prove the theorem. So let S be a subset of Rn, and may it be a non-empty and closed convex set. Non-empty and closed convex set. And y does not belong to, let there be a point y which does not belong to this set. Then there exists a unique point x0 in S with minimum distance from y. And further, x0 is the minimizing point if and only if this condition is satisfied. Y minus x0 transpose x minus x0 is less than or equal to 0 for all x belonging to S. So basically this condition should follow. Okay, so now let us reread this theorem. So let S be a subset of some n-dimensional real space, and it should be non-empty and closed convex set. So it should be closed and should be convex. And let there be a point y that does not belong to this set. So let's draw it. Let this be set S. Okay, and let us draw a point Y. Let this be the point Y we are talking about. This is non-empty and closed convex. So this is convex. You can see it is convex, and it is also closed. So closed means it should include its boundary points. So this red represents boundary points, and the set includes this boundary points. Okay, now so the theorem says that out of all the points from the set, there exists a unique point x0 which is closest to y. So what the theorem says, that there exists a point in S closest to y. It also says it is unique. You can see unique point with minimum distance. Okay, and the third thing that the theorem says, that in that point, if that x0 is that point, if and only if this x0 is less than 0, is satisfied for all x belonging to S. So let's say there is some point x. Next. So this is what the theorem says, that if there is a point outside set S and S is convex, then there exists a point x0 which is closest to that point, and also the so as you can see, the line joining the external point and x0, basically this vector, and the line joining any point in convex set S and x0 always form an obtuse angle. So basically their dot product is always non-positive basically, so they always form an obtuse or 90-degree angle. They never form an acute angle. So this is the geometrical interpretation of the theorem. Let's try to now prove this theorem. So we'll not line by line go through the proof. I'll just try to give you a proof sketch through which you will be able to prove the theorem. So let's assume what is given to us. So given S is subset of Rn, is a closed convex set, and Y does not belong to S. So we are given a closed convex set S and a point which does not belong to the set. Okay, so first what do we need to show? So first we need to show that there exists a minimizing point in there exists a point x0 in S which is closest to Y. Then we have to prove x0 is unique, and finally we have to prove that Y minus x0 and x minus x0 form an obtuse angle or non-acute angle for all x belonging to S. These three things we have to prove. So let's try to prove the first thing. So I hope you remember Weierstrass theorem, because that is what we are going to use. So what Weierstrass theorem suggests is Strauss theorem suggested tells us that if we have a closed bounded set S and x belongs to S, and we have a function f from S to R. Okay, and S is a subset of some n-dimensional real space. Then if S is closed and bounded, then we are definite to find a minimizing point of f in S. So we'll always find a minima of f in S. That is what Weierstrass theorem said. So here please note that S should be closed and bounded. That's what it meant. Now so how can we use this in proving this theorem CS1? So let assume a function. Let delta be equal to infimum of x belongs to S, x minus y. So for all x in S, we can define a function delta which is infimum of x minus y, where y is that external point. And also note that S is not bounded. So right now we cannot use Weierstrass theorem because S is not bounded. So what do? So we consider a different subset of S, which is consider the set S intersection ball of radius ball centered at y and of radius 2 delta. So basically, if delta is the minimum distance of y from set S, then we take 2 delta. So if I want to draw it, let me just copy this diagram. Okay, so what this is saying is let us have a ball of radius r and delta 2 delta radius Now this set is bounded. This set will be always bounded because intersection of a unbounded set and a bounded set. So this is a bounded set and this is an unbounded set. Unbounded and bounded. So intersection of those two sets will always be a bounded set. Correct? So this is now a bounded set. Now we can use Weierstrass theorem. So because we have a continuous function delta is a continuous function because it's a norm, like infimum of a norm, so it's a continuous function, and we have a set S which is compact, that is closed and bounded. So by Weierstrass theorem, there exists a minimizing point x naught in S that is closest to y. So existence is proved. That is x naught equal to arg min x belongs to S intersection of ball of radius y and radius 2 delta, ball at the centered y and radius 2 delta x minus y. So we have proved that there exists such a point. But so we have proven this first part. That first we need to prove there exists a point. So existence is proved. Now we have to prove the uniqueness. So what we have to prove is what is the guarantee that this is a unique point, unique minimizing point. So let's try to prove uniqueness. So what we'll do is we'll show uniqueness using triangle inequality. So, and what we'll do is we'll use the triangle inequality and we'll prove that there is not a unique point, and then we'll disprove this assumption. Okay, and we'll find that we'll get some contradiction, and then we'll disprove this assumption. That's what we'll do. So let there be some other point x hat belongs to S such that it also gives there are 2 points x naught and x hat which give the same distance delta from y. So y minus x naught and y minus x hat, both are at a distant y. Now since y is convex, since S is convex, x naught plus x hat divided by 2 will also belong to S. So basically if x naught and x hat are 2 points in S, then their midpoint will also belong to S because S is convex. Now we'll try to look at the distance of this point from the point y. So basically what happened is we can write by triangle inequality that 2 times y minus x naught plus x hat by 2. Let's say this is y, this is x, this is x hat, and this is the midpoint. Is less than equal to y minus y hat, y minus x hat plus y minus x naught. So this is the triangle inequality, right? So sum of these two lengths will always be greater than twice this length. Correct? So this is the triangle inequality. So, and now if this inequality is true, and this will be 2 delta, correct? So this is 2 delta. Now if this inequality is true, we actually have found a new point. Closest to y. But this is a like contradiction to our assumption that x and x hat, x naught and x hat are closest to y. So basically by contradiction, only equality should hold. Okay. So basically this in place of this inequality, only equality should hold. So that's what we are going to write. So that is only equality is true. That is y minus x naught plus x hat by 2 is equal to x minus x hat plus x minus x naught by 2 equal to 2 delta, which implies x naught, x hat and x naught plus x hat by 2 are all same, are all the same point. So basically this proves uniqueness. X naught is unique. So we have proven uniqueness also. So basically 2 points are done. That is, first we proved the existence, uniqueness. Now we have to prove this condition, that if x naught is that point, that if and only if this condition is true. So yeah, now let's prove the second part of the theorem. So what does second part of the theorem says? X naught is unique minimizing point if and only if y minus x naught transpose and x minus x naught is non-positive. Is non-positive, and for all x belonging to S. So for all points in X, the angle between the line joining any point in S and x naught, and line joining y and x naught should be a non-acute angle. So because it's an if and only if condition, it will be done in two parts. So first let's assume let x belong to S and y minus x naught transpose x minus x naught is less than 0. Let's assume this. Let's assume this and try to prove that x naught is the minimum distance, is at the minimum distance. Okay, so what is the distance of any point in the set S and y naught? So y minus x square. Okay, we can write this to y minus x naught plus x naught minus x whole square. And if we open it up, y minus x naught square plus x naught minus x whole square plus 2 y minus x naught and x naught minus x. So which we can write it as y minus x naught whole square plus x minus x naught whole square minus 2 y minus x naught transpose x minus x naught. Now by this assumption, we know this is an non-positive entity. So this term is always positive. Negative of a non-positive entity is always positive. So basically it's always greater than or equal to 0. Okay. What about the second term? X minus x naught. Because this is a norm, this is always positive. Correct? Positive or 0. So this is also greater than or equal to 0. Which means y minus x square is greater than or equal to y minus x naught square. Basically this. For all x belonging to S. Correct? Which means x is a unique minimizing point of y. Which means x naught is a unique minimizing point of minimizing point in S for y. This is what it means. So this is the first part. Now let's assume that x naught is unique minimizing point and prove this condition. So assuming that x naught is the minimizing point, which means mathematically that y minus x naught square is less than or equal to y minus z square for all z belonging to S. So this is what minimizing is. So x naught is the distance of x naught from y is lesser than all the distance of all the other points from y. Now consider any x. Consider any point in y. Consider any point x which is in S. Now since S is convex, the set of points lambda dot x plus 1 minus lambda x naught, this also belongs to S if lambda belongs to 0 and 1. This is the definition of convex set, right? Okay, so this also belongs to set S. Yeah. Now let's put this point in. Let this point be called Z and put this point in the above condition. So y minus x naught square less than or equal to y minus lambda x minus 1 minus lambda x naught square. Now let's try to simplify this. So y minus x naught square is less than or equal to y minus lambda x minus x naught plus lambda x naught square. Y minus x naught square gives y minus x naught minus lambda x minus x naught square. And now we can expand this. So this is the expansion, and we can see that these two cancel out, and what we are left with is lambda x minus x naught whole square is greater than or equal to 2 times pi minus x naught transpose x minus x naught. So remember what was lambda. So let's say, so what we said was, let x naught, if this is the convex set and y naught is some external point, x naught is the closest minimizing point, and x is some point in the interior of S, and z be some point here. So lambda changing lambda from 0 to 1 changes makes it move from x naught to x. That's what it does. So actually this is true for all lambdas belonging to 0 to 1. Which means it is also so if we can also set the limit lambda tends to 0 plus, by which the results follow that x y minus x naught transpose into x minus x naught is less than or equal to 0. So this is the result which we have proved, and hence the theorem CS1 is proved. Now let's geometrically look at relook at this theorem geometrically. So what does this say is, let's say we have a convex set S. Let's say we have a point y, external point y, and so there exists a closest point. There exists a closest point. It is unique. So x naught is unique, and it makes an obtuse angle. Makes an obtuse angle, or should I say non-convex angle, non-acute angle, sorry. Okay, so you can see so this is what this theorem says. Now let's move ahead and define something called separating hyperplanes. So all these things we are defining to get to Farka's lemma. So we want to define what are separating hyperplanes. So let's discuss what are separating hyperplanes. So as always, first I'll write the definition and then we'll discuss the definition. So let S1 and S2 be non-empty subsets in Rn, and H be a hyperplane, that is all the x which follow this equation A transpose x equal to B, where A belongs to Rn and B belongs to some real number. Be a hyperplane So I hope we discussed hyperplane in the previous lecture. So if you so this is the equations of the hyperplane. So basically, hyperplane is the equivalent of a plane in higher order dimension. So for example, in one so 2D, basically R2, a line is a hyperplane. In R3, normal plane is a hyperplane, and in higher order dimensions the linear equations represent something called hyperplane. So this is a linear equation. So I hope that gives you a quick overview of what hyperplanes are. We discussed it in previous lecture. So let's say S1 and S2 are two non-empty sets, subsets of Rn, and H be a hyperplane. Then the hyperplane H is said to separate S1 and S2 if A transpose X is greater than or equal to B. Let me write it in the bottom line. So A transpose X is greater than or equal to B for all X belonging to S1, and A transpose X is less than or equal to B for all X belonging to S2. So basically, this represents what means that all the points of S1 should lie on one side of the plane, and all the points in S2 should lie on the other half of the plane. So this is what separation means. Let's discuss what is strictly separation. So if A transpose X is greater than B for all X belonging to S1, and A transpose X is less than B for all X belonging to S2, then hyperplane H is said to strictly separate S1 and S2. So as you can see, this equality sign has been removed, correct? So that's what makes it strictly separating S1 and S2. Now there is something called strongly separating also. So what does that mean is the hyperplane H is said to strongly separate S1 and S2 S2 if A transpose X is less than or equal to B plus some epsilon for all X belonging to S1, and A transpose X is less than or equal to B for all X belonging to S2 for some epsilon belonging to this epsilon greater than greater than 0, basically positive scalar. Okay, so this is what strongly separation means. So I hope this gives you some idea, but to give you a better idea, let's look at them geometrically. So let's look at them geometrically. So if you see, here are two sets, S1 and S2. So S1 and S2 are two sets. They are closed set, you can see. So they include their boundary points also. And if we have a hyperplane H for which S1 is on one side and S2 is on the other side, then this is called separating hyperplane. We can also have the same sets which are not closed, and for this A transpose X less than B and A transpose X greater than B will be followed for X belonging to S1 and X belonging to S2. So no inequality sign will be followed. Here A transpose B greater than equal to B and A transpose X greater than equal to B and A transpose X less than equal to B for all X belonging to S1 and for all X belonging to S2. This will be true. What is strongly separating hyperplane? So there will be a hyperplane that it can be possible that S1 and S2 are they are getting separated from by a distance. So then that is called strongly separating hyperplane. So this hyperplane is strongly separating the two. Okay. Now we'll discuss. So this is the next result that we are going to discuss is an important result for discussing the Farka's lemma. So please pay attention. So what we are going to see is how does a hyperplane separates a closed convex set and a point. So in the previous section we saw how a hyperplane separates two sets. Now we'll see how does a hyperplane separates a closed convex set and a point. So let me write the result first. So let S be a non-empty set, empty closed convex set in Rn, and Y be a point such that it does not belong to this set S. Then there exists a non-zero vector A and a scalar B such that A transpose Y is greater than B and A transpose X is less than equal to B for all X belonging to S. So basically what this is saying, let's say we have a closed convex set and we have a point outside it, Y. Then we'll always find a hyperplane given by A and B such that point is on the one side and all the points in the convex side are on the other side. Okay, that's what it is saying. So intuitively it makes sense. Let's look it at geometrically once. So let this be the set S and this be a point Y0, Y. Okay, and this be the point X0. Okay, then this plane this hyperplane that I showed in the red dot, let me change the color of this line. So this red hyperplane H, you can see this separates the convex set on one side and the point on the other side. This can always be done through convex set. Note, this can't be done, this cannot be 100% done for a non-convex set, okay? Because if there is a non-convex set, and point, so this plane, if you can see, half of the points are on one side and of S, and half of the points are on the other side. On the other end, the point is on the other side only. So it can't be done for a non-convex set, but it can be said for a convex set. Intuitively, I think it makes sense, but let's prove it formally. And the proof of this theorem is really easy. So we'll use what we derived previously, that is, we'll prove theorem CS1. So by theorem CS1, there exists a unique minimizing point x naught belonging to S, such that y minus x naught transpose x minus x naught is less than equal to 0 for all x belonging to S. Correct? So what we'll do is we'll assume, let A equals to y minus x naught and B equals to A transpose x naught. Let us assume this. So what do we get? So we get A transpose x is less than equal to B. For all x belonging to S. How did we get this? So if we, from this we can get this result, right? Y minus x naught transpose x is less than equal to y minus x naught transpose x naught. So actually this is A and this is A, and so this whole is B. So this is how we got this relation. So this means that all of the point in set S are on one side, and the second relation that we want to prove is, let's look at A transpose y minus B. This, what is this equal to? Y minus x naught transpose y minus y minus x naught transpose x naught. This is what this means, right? And this can be written as y minus x naught transpose y minus x naught transpose, which is actually equal to norm squared of y minus x naught, which is always greater than equal to 0. Which is always greater than equal to 0. Greater than 0 because why is it not equal to? Because y can never be equal to x naught, so because y does not belong to S. So these 2 points prove these 2 boxes or these 2 results, and hence we can say that if there is a point and a convex set such that point is outside the convex set, that we can always find a hyperplane such that all the points in the convex sets are on one side and that given point is on the other side. Now let's define something what is called a cone. So a set K which is a subset to Rn, is called a cone if for all x belonging to k and scalar lambda greater than equal to 0, we have lambda dot x, that is just a scalar multiple of vector x, that also belongs to k. If that is true, then k is a cone. So before giving you some geometrical example, let me write one more thing. K is a convex cone if it is convex and a cone. So quite obvious that a cone is convex. A convex cone is a cone which is also convex. So that is very obvious. So let's give you some geometrical examples. So a ray like this, actually it's a cone. Okay. Two rays like this and nothing in between, no points in between, is also a cone. Similar, as you may have thought by now, any three rays are also a cone. Then we have something which looks like a cone, these two and all the area between. So this is also a cone. Actually this is also a cone, and a straight line, it turns out a straight line is also a cone, because like it has two vectors and it can, so a straight line is also a cone. But are all these convex? Let's look at this. So this is convex because any 2 points you take, the line joining those 2 points also belong in the set. So this is convex cone. This is a not convex cone because if you take these 2 points, the line joining the two does not belong to the set. So this is non-convex. Same with this 3. This is non-convex also. This point, this is actually convex because if you take any 2 points, the line joining those 2 points, the line segment joining those 2 points will always belong to the set. So basically this is convex. Is this convex? Unfortunately no. If you take these 2 points, the line segment joining those 2 points, not all points on that line segment belong to the set. So this is non-convex. And is this a convex set? Actually yes. So if you take any 2 points, so this will always lie in the set. The line segment joining those 2 points always lie in the set. So this is convex. So moving ahead, so this is where the definition of the cone ends. Now we'll look at the Farka's lemma. So let's discuss Farka's lemma. So let me write it first and then we'll discuss the lemma. So let A be a matrix belonging to R m cross n, and C be a vector belonging to Rn. Then exactly one of the following two systems has a solution. The first system is AX is equal to 0 and C transpose X is greater than 0 for some X, and A transpose Y is equal to C Y greater than equal to 0 for some Y belonging to R M Rn. So exactly one of these two will be true. Exactly one. So if one is true, the other will be false. If the other is true, the first will be false. At any time. So let's look at this lemma geometrically, which will give us a better explanation of what Farka's lemma is all about. So before starting, before going into the lemma, let's see what A represents. Okay. So let A1, A2, AM belonging to sub Rn, so column vector. So these are column vectors. Be some column vectors. Then we can define A as A1 transpose, A2 transpose, AM transpose. So basically what this means is A1, A2, A3 till AM are the rows of matrix A. Okay, so for example, if we want 3 cross 3 matrix, let's say, so A1 transpose this, A2 transpose this, A3 transpose. So let's say this be a 3 cross 2 matrix. So what this represent is 3 vectors in R2. So let's say A1, A2 and A3. Okay, so let's assume that A represents something like this. Then the geometrical interpretation tells us that let us draw these vectors first. This is A1, this is A2, this is A3. So what does X such that A transpose X less than equal to mean? What does this line means? So basically A transpose X less than equal to 0 can be written as A1 transpose X is less than equal to 0, A2 transpose X is less than equal to 0, A3 transpose X is less than equal A3 transpose X is less than equal to 0, which means all those X whose dot product with A1, A2 and A3 result in negative. So all those vector X which are an obtuse angle from A1, A2 and A3. So that's what this set means. So how will we find that? So let A1, everything between this line and this line will form an obtuse angle with A1. With A2 it will be everything between these lines, and with A3 it will be all the X's here. So what we are talking about is the intersection of these points. So intersection is here. Okay, so let us rub all the extra stuff and only represent this yellow part. So what does this mean is, okay, so all the vectors lying here lie in the curve, this xa transpose x less than equal to 0. Now let C be a vector. Okay, C be a vector here. We want to represent C transpose x is greater than 0. This is the first condition. Remember, this is this first condition we are talking about. This is A, this is C. Okay, so what does C transpose x greater than 0 represent? So it represents everything in this area, correct? So actually the intersection of these two will be this. Correct? So this is the area which represents. So the lemma says either this is true, or if C is on the other side, let me just copy this frame. So yeah, so either this is true, but if C is here, then C will be positive linear combinations of AI. So you can see that if I write a linear combinations of A1, A2 and A3 such that the coefficients are positive, so the vectors will lie only in this area, correct? Because only this area, the positives of A1, A2, A3 will lie. So if C is lies inside this area, then this is true. So I think this is the, what the lemma says, C either can lie inside this cone or outside this cone. So that's what the lemma is trying to say, and it's a very important lemma, and that will help us define the optimality conditions in various nonlinear and linear optimization. So let's try to prove this formally. This just I gave you a geometrical interpretation or an intuition of the lemma. Let's try to prove it formally. So this is the Farka's lemma. Let's again state it, that for any matrix A m cross n and a vector C R belonging to n, there exists only one solution. One of these condition is true, such that if Ax less than equal to 0 and C transpose x greater than 0, either or A transpose, there exists a vector y such that A transpose y equal to C for where y is greater than equal to 0, which means all the at least one of the components should be non-zero positive. All the components should be greater than equal to 0, and at least one of them should be all the components of y should be non-negative. That's what this means. Now let's try to prove. So how do we prove this? So what we'll do is we'll assume that one of these two solutions of one of these systems exist, and we'll prove that the solution for other system does not exist, and then we'll again do vice versa. So for the first thing, let's suppose system 2 has a solution. Let's assume system 2 has a solution, and we'll try to prove that system 1 does not have a solution. So what does that mean? That there exists a y equal to 0 such that A transpose y equals C. This is what it means, right? Now consider some x belonging to Rn such that Ax is less than or equal to 0. So this is true, like let's there be some x such that Ax is less than 0. Then we know C is equal to A transpose y, which means C transpose equal to y transpose A, correct? Which also means C transpose x equal to y transpose Ax, right? And because y is all the components of y are non-negative, and Ax we know that we have assumed to be negative, implies this is less than 0, which further implies that C transpose x is less than equal to 0. So which means system 1 does not have solution, because system 1 requires Ax less than equal to 0 and C transpose x should be greater than 0. But here we have proven the reverse. So when we assume system 2 has a solution, we have proven system 1 does not have a solution. Correct? Now let's try to prove the reverse. Let's assume suppose system 2 does not have a solution. Let's assume that. So what does that mean? Let S be a set x such that x is equal to A transpose y and y is greater than equal to 0. So let's assume that this is a set A. Okay, now so you can see that what does this set represent. So let's this be the set, and if y is all positive, we already discussed x will belongs to this set, and you can see this is a convex set. All right, so basically S is convex, and this is also closed because we are including all the points here on the boundary. This is a closed convex set. So I hope you understand that why S is a closed convex set. So S is a closed convex set. And C does not belong to S. Let's assume that there is a vector C that does not belong to S. C does not belong to S means we are assuming that second is not true. That's what it means, and that is because remember the second solution system is this, which says A transpose Y equal to C and Y is greater than equal to 0. So what we are saying that A transpose Y, let it be a set such that Y greater than equal to 0, and C does not belong to that set. Right? So this is how we say that the second system does not have a solution. That's what we want to say. So I hope that is clear. Now we can say by this that there exists a P in Rn and alpha in R such that P transpose X is less than or equal to alpha for all X belonging to S, and C transpose P greater than alpha. So how did we write this? So remember the theorem in which we said that if there is a convex set and if there is a point outside Y, then we can always find a hyperplane H for which the convex set is on one side and the point Y is on the other side. Just assume here that, and H was given by A transpose X is equal to B, correct? Now assume here A is P and B is alpha and your point is C and the set is S. So basically this theorem we are using here. So that if C does not belong to set S, then we can always find a vector P and a scalar alpha such that P transpose X less than equal to alpha for all X belonging to S and C transpose P greater than alpha. So basically C lies on the other side and the set S lies on the other side of the hyperplane H. So this result we'll use. So this means, the above means alpha is greater than equal to 0 since 0 belonging to S. So the thing is 0 belongs to S means because Y is non-negative, is greater than equal to 0, you can take all the Y's to be 0 and X can be 0 here. So if Y equal to 0, then X is 0. So basically that means that 0 belongs to set S, which means C transpose P is greater than 0. So this means that alpha is greater than equal to 0 and alpha can be 0 as well. So which means C transpose P is greater than 0. So let's take this as equation 1. Also from this equation we can see that alpha is greater than equal to P transpose X. Yes, and X we already know can be given by set S, that alpha is greater than equal to P transpose A transpose Y, right? Which is equal to Y transpose P A P, correct? For all Y greater than equal to 0. Now think of this as because alpha is finite, I mean think of it as alpha is a constant here. So for some point C, alpha will be a constant. So we do not remember alpha is a constant. Alpha is constant for given C and A, correct? But y can be as big as possible, right? So y can be anything. So because we are doing it for all y, so y can be very big. So alpha greater than equal to y transpose A P is possible only if AP is negative. Because think, if AP is positive and alpha is some constant, we can increase y arbitrarily. At some point this inequality will fail. So for this inequality to not fail for any y, AP has to be negative. It has to be non-positive. Okay, so AP is non-positive because y can be made arbitrary larger. Arbitrary larger. Okay, so that is the case, which helps us in saying that thus there exists a P belonging to Rn such that AP is less than equal to 0 and C transpose P is greater than 0. System 1 has solution. So basically we assume system 2 does not have solution, and we have proven system 1 has a solution. So if you have any question in this proof, you can ask me, because this is very important. And try to go through it once and try, and so then you'll get a better understanding. I'll share the notes with you. And so a few of the things you might not have understood, try to go through them yourself, and if you don't understand, you can ask me the question. Maybe if you're watching it on YouTube, you can ask me in comment section, or else if you are taking the lecture, you can ask me in the email. So this is the proof of Farka's lemma. There's one more results that comes from Farka's lemma. This is similar to Farka's lemma. It calls Farka's lemma corollary. So let me state it. So let A belonging to R M cross N, then exactly one of the following systems has solution. So first system of solution is AX is less than 0 for some X belonging to Rn, and second is A transpose Y is equal to 0, Y greater than equal to 0 for some non-zero Y belonging to Rn. So you can see we have removed C from here. I'm not going to prove this corollary in this lecture. Maybe I'll share a supplement or a note which contains its proof. Its proof is similar to Farka's lemma, so that's why I'm skipping it here in the lecture. If you want, I can add a separate video in which I'll prove this corollary. Okay, so yeah, so this is very similar to Farka's lemma, and we'll now move ahead. So now we'll discuss what are called supporting hyperplanes of sets at boundary points. So we will try to understand what are supporting hyperplanes. So again, I'll just state it and then I'll explain it to you. So let S be a subset of Rn and S not equal to 5. So basically S is not empty. Let x naught be a boundary point of S. A hyperplane H equals X such that A transpose X minus X naught equal to 0 is a supporting hyperplane of S at X naught if either S is a subset of positive half plane of H, I A transpose X minus X naught is greater than or equal to 0 for all S belonging to S, or S is a subset of H negative half plane half space is A transpose. I'm busy. वो meeting है. Okay. So let me explain it to you through a diagram. So let this be the set S and this point be X naught and this be the hyperplane through X naught. So what this theorem says is let S be some so S need not be convex here, as you can see there is no, and X naught be a point on the boundary point of S and a hyperplane X minus X naught. So basically if this is the normal at here and this is H, then this is a supporting hyperplane if either the set S lies entirely on one side of the hyperplane or the other side. Like this hyperplane should not cut the space. So it's so for example if I draw a hyperplane here the normal, as you can see, is in this direction. So hyperplane will be somewhere like this, and you can see it is cutting the set S. So this is not a supporting hyperplane. So I'll just rub it, and H here is a supporting hyperplane because set S lies entirely on one side of H. One more example that I want to share with you is let's say this is the point X naught. Okay, this is the point X naught, and this time it can also happen that this point goes like this, that it touches some other boundary point as well, but it still the set whole of the set S lies on one side of hyperplane S also. This is also a supporting hyperplane. It is not still not cutting the set S. So yeah, so this is what a supporting hyperplane looks like. So now we'll try to state two theorems and then we'll end the lecture. So theorem 1. Yeah, so let's discuss the theorem 1 first. So let S be non-empty convex set in Rn and x0 be a boundary point of S then there exists a hyperplane that supports S at x0. So what this theorem says is that let's there be a set S which is non-empty and convex. So if there is a convex set S and we have any boundary point x0, then there always exists a hyperplane which supports S. So this is highly intuitive. So let's say we have a convex set Y, a convex set S, and we have a boundary point x0, and then there always exists a support plane. So it's very intuitively clear, though we should prove this, but this is the proof of this theorem is very easy, so we are not going to prove it here. So for any convex set, if there is a point on x0, there is always a plane H, a hyperplane H which supports it. Basically support means all of the set S is on one side. Now the theorem 2 says that let S1 and S2 be two non-empty disjoint convex sets in Rn, then there exists a hyperplane that separates S1 and S2. Basically what this is saying is that if there are two non-empty disjoint convex sets, then always exists a hyperplane that separates S1 and S2. Basically, if there are two separates is the definition that we saw earlier. So so basically if we have two sets like this, two sets S1 and S2, so there always exists a hyperplane that separates the two. So let's say this and this. So there always exists a hyperplane that separates the two. So this is the theorem 2, and this also we are not going to do the proof because the proof is really easy. I leave it to you as an exercise. uh, now we end this lecture because we have come to the end of the convex sets. In the next lecture we'll go through convex functions, and yeah, so in the next lecture we'll go through convex function, and we use these definitions and theorem that we learned here in convex sets lecture. Thank you.